Now we are looking at electric circuits. So what we have to do first is to just reflect a bit on the work done in grade 10, which is basically the definition of terms in electricity and some other concepts. So we have the first term, which is resistance with a symbol R, defined as the opposition to the flow of charge. It has a unit ohm with that symbol. And another term is potential difference, which is commonly referred to as voltage, which is the work done in moving 1 coulomb of charge between 2 points in a circuit. The symbol is V, and V is equal to work done, which is W over charge Q. The unit is joule for work per coulomb for charge. So that unit, joule per coulomb, is called the volt with a symbol V. Then we also define current as a rate of flow of charge. Current is having a symbol I and is given as the charge over time, or delta T, and then it has a unit coulomb per second, which is called the ampere with a symbol A. Then this one is grade 11, which is Ohm's law. It states that the potential difference across the terminals of a conductor is directly proportional to the current, provided the temperature remains constant. So when we collect some data of current versus voltage applied across a conductor, and then plot the graph of current against voltage on the x-axis, we get a straight line. Now, when we find the gradient of this graph, the gradient is change in I, that is change in current, the horizontal increase, divided by change in V, the vertical increase divided by the horizontal increase, which is change in V. So that's our gradient. And then we see that if we find the inverse of the gradient, that's the reciprocal, 1 over the gradient, it turns this term upside down with the V now on top and then the I now at the bottom. Then that gives us a constant also. And that constant, that ratio of voltage, change in voltage divided by change in current, is called the resistance of the conductor or the wire involved. So we have the formula R is equal to V over I. That is, if we simply remove the delta from both the top and then the bottom, then it becomes R is equal to V over I, which is the mathematical representation of the relationship between resistance, voltage, and current. Now let us go to the lab and then investigate the resistors in series. Now we see a circuit with a 10 ohm resistor connected in series with a 30 ohm resistor. Now there is no current because the switch from we have a battery here that can supply 12 volts, but as it is now, the voltage across this resistor is 0 because the circuit is broken, the switch is open. So what we do now is that we see also an ammeter connected in series with the battery. This is switch, Then we have the connecting wires which connect to the 10 ohm resistor, then another connecting wire connecting. Then here we see another ammeter which is called a non-contact ammeter. This ammeter can be moved so that you can read the current at any point in the circuit. So let us close the switch and then see how the current behaves. Now, as soon as the switch is closed, you can see that the voltage is now 9 volts, which means that there's a current through this resistor, and the current is having a value of 0.3 amperes. Now, when we check the non-contact ammeter, which is also at a different point on the path of the current, it is also reading the same value of 0.3 amperes. So we can say that the current at this point of the circuit and the current at this point of the circuit is the same. Now let's just move the non-contact ammeter over to see whether the current changes. We see that the current is the same. Remember, current is the rate at which charges flow through the circuit. In other words, it's the speed or how fast charges flow through the circuit. So here, what this 0.3 amperes mean is that we have a charge of 0.3 coulomb flowing in 1 second, and you can see a visual impression of the electrons. Now we can change this circuit and then use circuit symbol so that you see the circuit symbol for battery is that, and then the circuit symbol for resistor is that, is this and that. So we can also use what you call conventional current. Now conventional current is the direction of positive charges. Now you can see that it's flowing, the long side of the battery is the positive side. So conventional current flows from positive through negative, but electrons flow, let's change to electrons. Electrons flow from negative to positive. That is one other thing that we need to learn. Then let us check the voltage of the 10 ohm resistor. We find that the voltage of the 10 ohm resistor is 3. That of the 30 ohm is 9. This one is 3. And then let's check the voltage of the battery. The voltage of the battery is 12. So you can see that if you add 3 and 9, you get 12, which means that these two resistors divide the total voltage of the battery, and they divide it proportionally, which means that the one that is having higher resistance gets a higher voltage, and then the one with a lower resistance gets a lower voltage. So let us remember that resistors in series divide the total voltage according to their proportion. They divide it proportionally according to their resistance, and these two resistors, the proportion is 10 is to 30. If we reduce it, we are going to get 1 is to 3. So they divide the voltage 1 is to 3. Then what we have to learn also is that how does resistance and current, how do they behave, or how do they relate to each other? So we are going to change the resistance of the circuit, and then we see how it affects the current. Now let me take the circuit back to the normal circuit, and then let me now vary the resistance of this circuit. Let me go for the 30 ohm. Now I'm going to use this slide to decrease the resistance to see how the current will change. Now I have started 29,5, 29, 28,5, 28, 27, 26, 25, 24. Now we can see that each time you decrease by 1 volt, the current increases by 0.01. So what happens here? Now 22, the current is now 0.37, and then as I decrease the resistance, the current is increasing. As I decrease the resistance, current is increasing. And then let me decrease it. Let me set it now to 0. There's no resistance. So current has increased to 1.2. So we can say that there's an inverse relation between current and resistance. As resistance decreases, current increases. And the opposite is true. When we increase the resistance, the current will start to what? Decrease. You can see as the resistance is increasing, current is decreasing. So that is what we can learn from here, the relationship between current and resistance. And what do we use resistor for in the circuit? In the circuit, we can see that resistance can be used to control the amount of current in the circuit. If we want high current, we have to lower the resistance. If we want low current, we increase the resistance. And then that is basically the main function of a resistor in a circuit, to control the amount of current. Now let's go to the board and then summarize all that we did in the lab. So we have a resistance for R1, that is a 10 ohm, is 10, and then R2 is 30. Now when you combine the two, you get 40 ohms. And the reason is that what it means that the total resistance of resistors in series is equal to the sum of the two resistors. Then, like we saw, the current is 0.3 ohm for R1, 0.3 ohm for R2, the 30 ohm, and then for the total resistance, the current is still 0.3 amperes, which means that the total current is the same as the current through resistor R1, and it's the same as the current through resistor R2, which confirms that these two resistors do not share the current. The current is the same. But what about the voltage? We saw that the voltage of the 10 ohm resistor is 3, and then that of the 30 ohm is 9. When you add them, you get 12. So we say that the voltage is divided proportionally between the two. Total voltage is divided proportionally, not equally, but proportionally, which means the resistor with a higher resistance will get a larger voltage, and so on. Then we see that the resistance is what? Directly proportional to the voltage. We have seen that one. The one with a higher resistance will have a higher voltage, and then resistance and current, we see that resistance is inversely proportional to current. That is, as we increase the resistance, the current decreases, and as we decrease the resistance, the current increases. Then we come to power. We have three formula for calculating power. The first one is power is equal to IV, that's current times voltage. The second one is I square R, and the third one is V square over R. Now each of these, when you use them, you will get the same result. So for the first formula, the current here is 0,3 and the voltage is 3. So when we multiply, we get 0,9. If you use the other formula, you use current, you square it, multiply by the resistance, you get 0,9. It's the same thing. Any formula that you use to give you the same answer. And that is how to calculate the power for the 10 ohm. Then let's come to the power for the 30 ohm, which is IV. The current is still 0,3 and the voltage now is 9. So this one is going to have a higher power. And you can see that 0,9 and then 2.7 watt they are in proportion. We'll be looking at that one. Then if you use the other method, the other formula, I square R, you will see current square times resistance, you get this. And then if you use this one, voltage square, 9 square divided by 30 gives you the same 2.7. So we say that the power of resistors in series are in direct ratio of their resistance. The ratio of the resistance is 1, R1 is to R2 is 1 is to 3. That is 10 is to 30. If you reduce it to the lowest, the simplest ratio is 1 is to 3. And then if you divide the power, or the power of the two resistors are also in ratio of their resistance, which is also 1 is to 3. Now what this means is that the total power, for the total power of the circuit, the 10 ohm resistor is taking one part, and then the 30 ohm resistor is taking 3 parts, which is 75% of the power, and then this one is taking 25% of the power. So this is what we need to know about resistors in series.